To solve problems involving volumes of gases not at STP in chemical reactions, we need to combine the ideal gas law with stoichiometry. In earlier lessons, I've introduced and used this stoichiometry island diagram. The left and right sides here are mirrored. The middle island on the outside is volume of gases at STP. And to get from that island, or on the other side, to get to this island, we need to use the relationship that 1 mole of any gas takes up 22.4 liters of space. We are not able to use either of those volume islands when the conditions for a gaseous reaction are not at STP. And that's what we're going to run into in this lesson. So let's try this one. What volume of hydrogen reacts with carbon at 981 torr and 334 degrees Celsius to yield 42.0 grams of N-pentane, where N stands for normal pentane. N-pentane or normal pentane simply means that your 5 carbon atoms are all in a single line. To find the formula of N-pentane, I think you can figure this out. If you can see in front of you 5 carbon atoms in a row, 1, 2, 3, 4, 5. Above those 5 carbon atoms you have 5 hydrogen atoms, and below those 5 carbon atoms you have 5 hydrogens. That's 5 hydrogens on the top, 5 hydrogens on the bottom, and then 1 on each end. That's a total of 12. Pent meaning 5 carbons, and for normal pentane you will have 12 hydrogens. Okay, well, let's write a balanced equation because we can't do stoichiometry without a balanced equation. Hydrogen is diatomic, and then carbon simply C, and there's our formula for N-pentane. Let's balance that. We look here and see that we are not at standard temperature and pressure. If we draw a little model of our island diagram, we start at 42 grams of normal pentane. So we're going to start up here at mass island for the pentane, and we might think, oh, well, we need volume of hydrogen. The right side of the diagram represents hydrogen. The left side, this represents pentane. But we can't go to that island because we're not at STP. So instead, we're going to have to go to this island, which is moles of hydrogen. And once we have moles of hydrogen, that's the variable N in our ideal gas law equation, then we can use the pressure and the temperature to find the volume of hydrogen. So let's go ahead and move from grams of pentane, which is the green circle up here. We're going to need 1 conversion factor to go to moles of pentane, and then 1 conversion factor to go from moles of pentane to moles of hydrogen. I just wrote NP for normal pentane instead of C5H12 because it takes up less space. In any case, we can find the molar mass of normal pentane to be 72 grams, and the ratio from the balanced equation between moles of pentane and moles of hydrogen is 1 to 6. That yellow triangle has a value of 3.5 moles of hydrogen. We're going to use the ideal gas law. We need to calculate volume, so let's divide both sides by P, and let's start putting our numbers in. We know how many moles of hydrogen. I'm going to use the gas constant of 0.08206. Now, that's the one that goes with liters for volume and also atmospheres for pressure. And our pressure isn't given in atmospheres, but we don't have an R value for torr, or millimeters of mercury. So we're going to take care of that in just a minute. Here's our temperature, 334, but it's not quite our temperature because it of course has to be in Kelvin. So there's our temperature, 334 plus 273. And then in the denominator, we said that because our R value is matched up with atmospheres, we're going to change this torr into atmospheres. We could do it in a separate step, but I just included it right there in the entire equation, and when we solve that, we get a number like 135 liters.